Okay, hello everyone. So in this video, we'll be looking at an exercise where we're asked to design a decision procedure for a decision problem about regular languages. In this particular video, this decision problem is about regular expression equivalency, and in particular, it asks um, given regular expressions r1 and r2, where we have these regular expressions defined over some non-empty alphabet, is um, for these two particular regular expressions, r1 and r2, that were given, r1 concat r2 equivalent to r2 concat r1. So essentially what's going on is we're given two regular expressions as the input in our decision problem, and the expected output in this decision problem is we should return true or yes if the language denoted by r1, r2 is equal to the language denoted by r2, r1, and we should return false or no if this is not the case. So if the language denoted by r1, r2 is different from the language denoted by r2, r1. Okay. Okay. And so in general, before we start this, I just want to say that in general, this is false. In general, r1, r2 equiv r2, r1 is false, right? Why? Because suppose r1 is just the atomic regular expression A, r2 is the atomic regular expression B, then, I mean, it's definitely not true that the language denoted by AB, which is the set of strings that just contains AB, is equal to the language denoted by BA, which is the set of strings that actually just contains BA, right? These are clearly different, which means that their corresponding regular expressions are by definition not equivalent. But it's still possible that this happens, right? If it's false in general, it doesn't mean that it's always false. Like for instance, so it can sometimes be true. For instance, suppose that R1 and R2 are the same, right? So for instance, they're both equal to A. Then I mean for sure, yeah, L of R1, R2 is L of AA, which is the set that contains AA, which is going to be the same as L of, let's put it here, L of R2, R1, because this is L of AA again, right? And so essentially what we're trying to do is we want to design an algorithm where instead of having to check this manually, the algorithm just does it for us. Okay? So that's kind of what we're looking for. So how are we going to do this, right? Essentially, we kind of need to design an algorithm which checks whether uh, I'll write R2, R1, R2 equiv R2, R1. Or really, in other words, if we're talking about like their corresponding languages, the language denoted by R1, R2 is exactly the same as the language denoted by R2, R1. Okay, so this is what we're kind of looking for. So this is a bit difficult to sort of do immediately, right? It might be difficult to design an algorithm which studies the regular expressions, the symbols within the regular expressions, and then determines just based on like reading the regular expressions, whether or not they're going to be equivalent. That kind of sounds pretty hard. So maybe a good idea might be to convert these things to FAs. Because when you convert things to FAs, then you can start checking the equivalency between two DFAs. And you can do this much more sort of easily when the DFAs are both minimal DFAs, right? Because you have less states to check, and actually you might not run into problems if you're comparing pairs of minimal DFAs. So I think that's the sort of path we should go towards. So um, the sort of crux here is to try to convert this to a problem about FAs. Okay. So, well, how am I going to do this? Well, I know how to convert from a regular expression to its corresponding FA, right? So I know that there are these atomic regular expressions that correspond to sort of atomic building blocks in FAs, and you can sort of build these up together using epsilon transitions and sort of self loops, right? So in particular, if I want to convert r1, r2 to an FA, let's call it to an FA M1, then what I can do is, well, I know that there's a corresponding FA for R1, let's call it N1, and a corresponding FA for R2, let's call it N2. And so then the FA for R1, R2, that's just going to be the concatenation of these two machines, right? So that's actually just going to be the start state of N1, right? Which is then going to connect with epsilon transitions to the start state of N2. And remember, we're going to be doing, to do this correctly, you kind of have to make the accept states in here non-accept states, right? So you're actually attaching from the accept states in N1. So these become non-accept states. And you're attaching to the start state of N2, right? So here we're assuming that N2 has a single start state. And then you're keeping, okay, that's not super clear. And then you're keeping the accept states in N2, right? So then let's start from like the regular expression logic. If I have a string, so if I have a string W that's described or that matches with R1, R2, then what does that mean? That means that it it's broken into two parts, UV, where U is described by R1 and V is described by R2, right? So that means that um, since we know that we have equivalent um, FAs corresponding to regular expressions, and that means that N1 accepts U and N2 accepts V. So if you feed in UV into this machine, then you'll read U and you'll get to what was the accept state of N1, but which is now just a non-accept state. But I know that I'm actually going to get there because originally N1 would have accepted U. So it would have landed in an accept state. Then I can jump to the start state and then read V. And I know that when N2 reads V, it gets to an accept state, right? So then I know that in the end, I would end up in an accept state of M1, right? Of the sort of bigger FA that concatenates the FAs of N1 and N2. And then the logic is the same, right, for R2, R1. So you'll also convert R2, R1 to an FA M2, right? And so I'm just going to depict it like this. I'm going to be a bit less detailed. So I'm going to have N1 and then epsilon transitions, N2, and then my accept states, right? You might pull out the accept states. You might like in some conversion algorithms, you also make these non-accept states, and then you have a single one with an epsilon transition. I mean, it's all the same, right? I think what I'm trying to convey is that it's definitely possible to create FAs for L of N1 concat L of N2, and L of n2 concat L of n1. So I think hopefully you're convinced by this. Okay. So now I have my two FAs, and now really the question becomes, um, is L of M1 equal to L of M2? Right? This is the new question that I'm trying to answer. And now this is kind of nice because maybe M1 and M2 are NFAs, in which case it's probably tricky to ask this question because it's kind of hard to map these things and you might run into problems because of non-determinism. So what I can do then is I can determinize, or let's just use the noun. Um, Although I think determinize, something like that. Convert M1 and M2 to DFAs. So let's call them M1 prime and M2 prime. Now at this point, you're not going to run into problems of non-determinism if you're going to try to sort of create a mapping between the the two machines, but you still might run into problems even with just DFAs because it might just be that the machine M1 is huge and the machine M2 is quite small, but maybe they accept the same languages. It's just a matter of like them having a different number of states. And so to avoid this problem, what we're going to do now is to minimize. So we're then going to minimize M1 prime and M2 prime to minimal DFAs, M1 prime prime and M2 prime prime. And now what's nice is minimal DFA are unique. DFA are unique. So that means, right, that what does this mean, right? Minimal DFAs are unique means that if I had started with two different looking DFAs, which accepted the same language, when I minimized them, then I would have gotten exactly the same machine. Maybe just the like names of the states would have been different, but in terms of like the architecture of the machine, they would have been exactly the same. And so that means that at this point, it should be quite straightforward to check whether M1 prime prime and well, it'll be it's like the right moment to actually check whether the two DFAs are the same, right? Because if they're not the same at this point, then that means that they were not actually accepting the same language. So at this point, I can check whether L of M1 prime prime is equal to L of M2 prime prime. And to do this, right, to do this, I don't have to like go through each of the strings in sigma star and check whether when M1 accepts it, M2 also, when M1 prime prime accepts it, M2 prime prime also accepts it, and so on. I don't have to go through like what would be an infinite loop. Instead, I can just look at the state transition diagram, right? So, and in particular, if I have like two tables, maybe, so if I have two tables, um, something like this, let's give the states different names so that it's not trivial. Then I can just check, right? I can check whether L of M1 double prime is the same as L of M2 double prime by checking whether M1 prime prime is equal, really for the mathematicians, I mean isomorphic, but let's just say M1 double prime is equal to M2 double prime. And how do you sort of do this procedurally? Well, you start at the start state. So you start at the start state. Oh, my pen is not. Okay. You start at the start state and then you check, okay, um, when I read A and B, so when I read A and B, I go to two states. So when I read A and B, I go to two states. So when I read A and B and I go to these two states in both cases, these states are going to be called different things probably. So maybe like Q1, Q2, and S2, S1. And so maybe it's possible that uh, this is in fact the same transition. It's just that the mapping or the bijection that exists between these two guys is, Q0 is S0, Q1 is S2, and Q2 is S1. So then at that point, and sort of this is the case for all of the rows here. So at that point, this kind of becomes, there's like a few ways of determining whether um, these two tables represent the same thing. You can first think about this as kind of like a graph isomorphism problem, maybe. So like you have a Q naught and you have S naught. So, I mean, I know what the start states are, right? So the start states are Q naught and S naught. So these two definitely have to be paired, right? And then what I could have something like maybe A goes to S2, and then B goes to S1. Oh, sorry. A goes to Q1, and B goes to Q2 for the left table. And then S naught with an A goes to S1, and with a B, or sorry, S2, and with a B goes to S1. And then I can fill in the transitions for like Q1 as well, Q2. So basically like reconstructing the state transition diagram and using Q naught and S naught as like an anchor, then I can kind of check if these two graphs are the same. So then it might become like a graph isomorphism problem. So this is not a video about graph isomorphisms and the algorithms related to them. But if you know an algorithm for graph isomorphism, then that should convince you that, oh, I could use this, and then I could check whether these two tables are the same. Another way that you could do this, which is more brute force, but I think is more intuitive as well, is so this would be one way of checking that M1 prime double prime is the same as M2 double prime. The other way, uh, right? The other way might be to check M1 prime equal M2 double prime is just like a brute force approach. A brute force approach where you try every possible pairing. Try every possible pairings between the states in Q1 and Q2. So what do I mean by every possible pairing? Well, in this case, I know that Q naught and S naught have to be paired together because they're both the start states. But now I have two possibilities. Either Q1 and S1 are paired together, and Q2 and S2 are paired together, or Q1 is paired with S2, and Q2 is paired with S1, right? So I have two possible bijections that exist, right? And now I can essentially check if I were to replace S naught with Q naught, S1 with Q1, S2 with Q2, here and also everywhere here, would I get exactly the same table? If yes, then that's great. That means that I actually do have a bijection, right? If no, then maybe this first pairing was incorrect, right? So then I'll try the second pairing. If there the second pairing yields the same table, then that means that again, oh, actually I did have a bijection. So there is a way to like rename things such that I get exactly the same state transition diagram. If no, then that means that however I kind of map between the states, I'm just doing different things, right? I'm doing different things. And so that would tell me that no M1 double prime is not the same as M2 double prime. Okay. So basically what I've discussed is like small subroutines for each of these kind of steps here. Now, the last thing I'm going to do is just put these all together, omitting some of the detail because I've explained it kind of here, right? So the full algorithm for the decision problem Rex equivalent, which as a reminder is, R1, R2 equivalent to R2, R1. So this algorithm operates on inputs of type regular expression, R1 and R2. So the first thing that we do is we convert R1 and R2 to FA, M1, and M2. The second thing we do is we take the FA concatenation of M1 with M2. So I'm just representing, this is like, I'm abusing notation, but I'm representing the sort of uh, concatenation of two FAs with epsilon transitions as M1 dot M2. And I'm going to assign this to M1 prime. So this is overloading notation. Sorry about that, but this is CS, and so that's what we do. Then M2 prime, that's going to be for M2 M1. Now these might be, well, actually these are definitely NFAs because they have epsilon transitions. So then what I'm going to do is I'm going to convert M1 prime and M2 prime to DFA. So then I get, okay, now I have, it's a bit of a problem because M1 double, well, okay. So now I get M1 double prime and M2 double prime. These are just like different from the M1 and M2 double prime here. Then I'm going to minimize M1 double prime and M2 double prime to get triple prime. So M1 triple prime and M2 triple prime. And then I'm going to check if M1 double prime triple prime is equal to M2 triple prime using the brute force technique or the sort of graph isomorphism technique. Then I return true, right? Then I return true because it does mean that um, the FAs for these two guys do accept the same language, and so um, their corresponding initial regular expressions, R1, R2, and R2, R1, describe the same language. Otherwise, I return false, right? Because it means that um, I don't have the same, I'm not accepting exactly the same strings here, which means that I'm not accepting the same strings here, right, between these two guys. And so that means I'm not accepting the same two strings between these two guys, which means that R1, R2, and R2, R1 are not describing the same language, right? And so this is the pseudocode that gets you a decision procedure for this decision problem. There were a few other ways of doing this, but notice that one way that wouldn't have worked is if you had said something like so if you had said something like for W in sigma star, check if R1, R2, if W matches with both R1, R2, and R2, R1, or does not match with both. If this is true, then continue in this for loop. Right, so this something like this, right? Right, if this is true, then that means that for this W, there's no reason to say that the regular expressions are different. Otherwise, well, that means that there is a difference, right? W might match with R1, R2, but not with R2, R1, or vice versa. Else return false. So it might, if it doesn't match, return false. But if the two regular expressions are equivalent, then this for loop is just going to loop forever, right? It's always going to say continue here, right? Because it's always going to find for every string, it's going to say, oh, well, I either match with both or I don't match with either because they're the same, right? So this infinite for loop doesn't work. And so instead, what we have is we have like a finite procedure for what at first glance seems like an infinite loop. So here we've become like we've created sort of a finitely sort of we've taken a procedure that never finishes and created a procedure that finishes in finite time, right? So that's quite a feat in and of itself. Okay, and so this was how you could design. This was one possible solution to um, designing a decision procedure. That's what we did. That solves or decides this decision problem.